Train shunt resistance. Train shunt resistance is the highest resistance which, when connected across the track, drops the track relay. To ensure safe working of a track circuit, a higher value of TSR is desirable. In a closed track circuit, the track relay is normally in energized condition and the front contacts are closed. When TSR is connected across the track, track relay drops and its front contact opens. We can connect TSR anywhere between feed end and relay end. For DC track circuit, the minimum permissible TSR value is 0.5 ohms. Drop shunt resistance. Drop shunt resistance is the highest value shunting resistance that can cause the track relay to drop. It is desirable to drop the track relay even with much higher resistance. Pickup shunt resistance. Once a track relay drops, it takes some minimum voltage for the relay to pick up again. Pickup shunt resistance is the least value of resistance with which the track relay picks up. Importance of pickup shunt and drop shunt resistance on a closed track circuit. In longer track circuits, sometimes effective shunting by a lighter vehicle may not take place throughout their length. At vulnerable points, the track relay may again pick up momentarily under occupation. This may be due to rusty rails in a portion of track on less frequently used lines. This may also be caused by the drop shunt being of critical value and the ballast condition in the track not being uniform. So, it is necessary that at the time of installation and often during maintenance, the pickup shunt value is also noted for such track circuits. Ballast resistance. Ballast resistance is the combined resistance offered by ballast and sleepers. The ballast resistance acts parallel to track circuit. It is the resulting resistance of all small parallel resistances acting across a track circuit. How does ballast resistance affect relay voltage? When the resulting ballast resistance is high in given track circuit, the leakages through ballast are very less or almost nil. Hence, full voltage applied at track feed will pass through rails without much drop, and thereby track relay gets maximum voltage. That is, the relay voltage is directly proportional to the ballast resistance. So, for better performance of the track circuit, high or infinite value of ballast resistance is desirable. How to measure VF and IF? An approved type of digital multimeter is used to measure VF and IF. Connect multimeter to the disconnecting link's terminal as shown on the screen. How to measure VR and IR? An approved type of digital multimeter is used to measure VR and IR. Connect multimeter to the disconnecting link's terminal as shown on the screen. How to calculate ballast resistance? Ballast resistance is equal to average rail voltage by leakage current. Minimum permissible ballast resistance for track circuits 2 ohm per kilometer within the station yard, 4 ohm per kilometer outside the station yard. Do's and don'ts. Provide proper drainage throughout the track zone. Keep the ballast clear of rail at least by 50 mm. Provide GFN liners and rubber pad for PSC sleepers in track zone. Rail and bond resistance. Rail and bond resistance is the combined resistance offered by rail and bond. Rail and bond resistance is equal to voltage drop in rail by average track current. Normally, rail and bond resistance does not vary. Rail and bond resistance should be at the rate 1 ohm per kilometer. Relation between train shunt resistance, ballast resistance, relay voltage, relay resistance and regulating resistance. For more details, click on the links given below. RB versus TSR. RB is the combined resistance offered by ballast and sleepers. TSR is the highest resistance which, when connected across the track, can drop the track relay. From the graph given on screen, we can conclude that an increased ballast resistance of a track circuit causes a decrease in train shunt resistance value. VR versus TSR. VR is the track voltage at relay end. TSR is the highest resistance which, when connected across the track, can drop the track relay. From the graph given on screen, we can conclude that an increased track voltage at relay end causes a decrease in train shunt resistance value. RR versus TSR. RR, that is relay resistance, is the resistance offered by relay coil. TSR is the highest resistance which, when connected across the track, can drop the track relay. From the graph given on screen, we can conclude that up to about 40 ohm relay coil resistance has an improving effect on the TSR. Beyond that, if the relay resistance RR is increased, TSR starts falling. RT versus TSR. RT, that is regulating resistance, is the resistance offered by regulating device. TSR is the highest resistance which, when connected across the track, can drop the track relay. From the graph given on screen, we can conclude that, similar to relay resistance increase in regulating resistance RT results in an increase of TSR, but beyond certain a limit it starts decreasing. RB versus VR. RB is the combined resistance offered by ballast and sleepers. VR is the track voltage at relay end. From the graph given on screen, we can conclude that RB, ballast resistance, is directly proportional to VR, relay voltage. RB, VR, TSR. RB is the combined resistance offered by ballast and sleepers. VR is the track voltage at relay end. TSR is the highest resistance which, when connected across the track, can drop the track relay. From the graph given on screen, we can conclude that an increased RB, ballast resistance, of a track circuit causes a decrease in TSR, train shunt resistance, and increase in VR, relay voltage. Length of a track circuit. For more details, click on the links given below. In station yard, maximum length of any track circuit is 670 meters. Outside station yard, maximum length of any track circuit is 1000 meters. In RE area, maximum length of any track circuit using QTA2 relay is 350 or 450 meters. In RE area, maximum length of any track circuit using QB80 relay is 750 meters. Relays. For more details, click on the links given below. For track circuit up to length of 100 meters, shelf type track relay of 9 ohm resistance is used. For track circuit having length more than 100 meters, shelf type track relay of 2.25 ohms resistance is used. For track circuit up to length of 100 meters, plug-in type QT2 relay of 9 ohms resistance is used. For track circuit having length more than 100 meters, plug-in type QT2 relay of 4 ohms resistance is used. In RE area, irrespective of length of track circuit, following relays are used. These are AC immunized 9 ohm relay, QT80 relay of 9 ohms, QB80 relay of 9 ohms. Choke. In RE areas, a choke is to be provided in series with negative rail both at feed end and relay end. Choke enhances the immunity level of track relay. It also blocks AC voltage coming from track to relay. Insulation resistance of PSC sleeper. Insulation resistance between any two inserts of PSC sleeper should not be less than 500 ohms. A sensitive multimeter of not less than 20 kilo ohms per volt resistance of coil is used to measure insulation resistance of PSC sleeper. We make use of 4 inserts, that is A, B, C and D, to measure insulation resistance as shown on the screen. Steps to measure insulation resistance of PSC sleeper. Connect multimeter across inserts A and B. Note the reading. Connect multimeter across inserts A and C. Note the reading. Connect multimeter across inserts A and D. Note the reading. Connect multimeter across inserts B and C. Note the reading. Connect multimeter across inserts B and D. Note the reading. Connect multimeter across inserts C and D. Note the reading. The lowest of these readings will be considered the PSC sleeper resistance. Glued rail joints. Glued joints are inserted by the engineering department as per the requirement. In Indian Railways, 2 types of glued joints are used. G3L type having 6 bolts. G3S type having 4 bolts. Glued joint consists of insulating bush, insulating liner, adhesive layer, fish plate, washer, nut and bolt. Insulation resistance of glued joint. In dry condition, insulation resistance of glued joint should not be less than 25 mega ohms when measuring voltage of 100 volts DC is applied across the joint. In wet condition, insulation resistance of glued joint should not be less than 3 kilo ohms. 100 volts DC measure is used to measure insulation resistance of glued joint. Measurement of insulation resistance of glued joint. Insulation resistance of glued joint can be measured by applying a measure between fish bolt and rail, fish plate and rail. Traction bond. The following bonds are provided in track circuit zones of AC 25 kV RE area. Transverse bond or Z bond, cross bond, structural bond, longitudinal bond. These bonds provide easy path for traction return currents, ensure safe working of the track circuit, ensure safety of working person. Transverse bond. Transverse bonds are provided between negative rails at every block joint. Transfer bond facilitates passing of traction return current ahead from one track circuit to the other. It helps in detecting a block joint, insulated rail joint, failure between the two track circuits. Cross bond. Cross bonds are provided between negative rails of adjacent track. It avoids interference of uninterrupted flow of traction return current with track circuit. Structural bond. Structural bonds are provided in between negative rails and fixed traction structures. Structural bonds are provided between traction mast, traction substation, negative, and negative rail of track. Longitudinal bond. Longitudinal bonds are provided at fish plate rail joints for continuity of traction return current through negative rails. Longitudinal bond need not be provided for welded rail joints. Stray voltage and stray current. In the vicinity of electrical installation such as power station, stray currents are prevalent in the earth. Stray current and stray voltages may prove to be fatal for safe working of DC track circuit. In DC track circuit area, rails are insulated from ground and thereby voltage may develop across the rails and earth. If this voltage is in the favorable direction of track circuit feed end, the same voltage appear at track relay and this may prove to be unsafe. So, before installation of DC-TC, the presence of stray voltage and current are to be checked. For any length of track circuit, stray voltage should not be more than 100 millivolts. For track circuit length less than 100 meters, stray current should not be more than 10 milliamperes. For track circuit length more than 100 meters, stray current should not be more than 100 milliamperes. Measurement of stray current. Connect two suitable types of milliammeters as shown in the diagram and take simultaneous reading at A and B. Record the readings at different periods of time, that is, morning, afternoon, evening, and extend the test for 3 days so that maximum value can be obtained. Measurement of stray voltage. Measure voltage across resistance R at point A and point B as shown in the diagram. Record the readings at different periods of time, that is morning, afternoon, evening, and extend the test for 3 days so that maximum value can be obtained. Remedies: if stray current and stray voltage are not within safe permissible limit. Reduce the length of a track circuit. Interchange relay end and feed end, that is, make the direction of feed current opposite to that of stray current. If still problem persists, use different types of train detection devices like axle counter, AFTC, etc. Track circuit arrangement. In RE area, only single rail track circuit is adopted. Negative rail is common for both track circuit negative and traction return current. In non-RE area, double rail track circuit is adopted. Both the rails are used for track circuit. Percentage release of track relay is equal to drop away voltage by pickup voltage. Percentage release of track relay should not be less than 68%. This table consists of all parameters of track circuit for non-RE area. Table consists of all parameters of track socket for RE area shown on the screen.